Swayam Prabha. Digital India. Educated India.
Welcome to the course Analysis of Variance and Design of Experiments. So, you can recall that in the last lecture we had talked about CRD, that is completely randomized design. And in that case we had understood two parts. One thing is the how to conduct the experiment and how to collect the data, and second part was how to conduct the analysis of variance. So, now if I try to merge both of them together, means I can say in very simple language that how to collect the data which is compatible for the test of hypothesis in the one-way classification. And you had seen that completely randomized design is more suitable when you have homogeneous experimental material and the variability is being caused primarily by only one factor. But in practice there can be many situations where the heterogeneity is present in the data, and in that case you have to do something so that you can reduce the random error, and you have to conduct your analysis in such a way such that you take care of those factors which are known to you that are going to cause the variability in the observation. So, in this lecture we are going to talk about randomized block design, and this randomized block design is based on the two-way analysis of variance. So, you already have learned that how you can develop the test of hypothesis for two-way analysis of variance. So, now we are going to address how the data is going to be collected such that it satisfies the basic assumptions of the two-way classification and it is compatible with the requirements of the test so that it can give us a good statistical conclusion. So, now if you try to see in the last lecture I had taken an example where we had considered different doses of medicine, say 1 tablet, 2 tablets, 3 tablets, and which are going to be given to a group of patients. Now, in the case of CRD, you had simply taken the medicine and given it to any of the patients at random, right. But don't you think that the age of the patient is also going to influence the effect of medicine? For example, if you try to give a higher amount of medicine to a young child, and if you try to give the lower amount of medicine to an elderly person, that may have very little effect, or there may be some reactions also. Well, this is the information which is coming to us from our common sense. Nobody has told us. As I always say that God has given us a component in the mind which helps us in doing statistics without even knowing it. But now if you try to see, when you are trying to conduct the experiment, or if some medicine company asks you to conduct the experiment and inform them that what is the efficiency or the efficacy of the medicine, don't you think that you should first group the patients with respect to their ages, and then try to give the different quantity of doses or different quantity of medicines to these groups? So, now if you try to see in the example of medicine, you are first trying to group the patients into different age groups, and you are trying to see that the ages of different people in that group should be as close as possible. There should not be a big amount of variation in the values of ages within a group. For example, one can choose the age group of say 5 years to 10 years and say this year 10 year to 15 years to 20 years. So, we believe that well, there is going to be some variation between the age of a 11-year-old young child and a 12-year young child. They are going to be similar more or less. The variation is going to be very, very less. Similarly, if you try to take an elder person of say 27 years old and 28 years old, well, there can be some variation between them, but more or less the variability is not going to be great. On the other hand, if you try to take a young child of say 7 years, 8 years old and elder person of say 27 years to 28 years old, and if you try to put them inside the same group, the variability is definitely going to be very high. So, this is what I mean when I say that we are going to first group the experimental units in homogeneous groups, and these groups in the case of design of experiment, they are called as blocks. So, we are simply trying to divide the entire experimental material into different blocks, and these blocks are going to be constructed in such a way such that the experimental units which are within the group, they should be as homogeneous as possible, and the experimental units which are between the groups or say across the group, the variation will be higher. Well, you have to understand one thing, that whenever we are trying to conduct any statistical experiment and based on that we want to analyze the data, our objective is to give the statistical inferences and conclusions which have got the smallest variability. So, we try to control the variability at every stage, so that at the end we have the smallest possible variability, which is obtained to the best of our capability, to the best of the capabilities of the statistical tools also. So, that is what we are trying to implement it here. So, now when you are trying to group those experimental units into different blocks, obviously the design is going to be called as a block design. And now these blocks have to be constructed in such a way such that they are within homogeneous, and then you are trying to allot different treatments to different units inside the blocks and in all the blocks. So, this is the setup of randomized block design. Well, there are some more specifications which I will be explaining you when I start my slides, but these are the basic structures. And in this experiment, if you try to see, there are going to be two types of factors which are going to affect the outcome. First factor is block effect, means how are you going to create the blocks. And then second factor here is the dose of the medicines. For example, you are trying to take 1 tablet, 2 tablets, 3 tablets, etc. So, now there are two factors which are going to affect the outcome. So, now if I ask you what type of analysis of variance is going to be suitable in this case, so now we have an answer. There are two factors, so we are going to use here the two-way classification. Now, under the setup of this randomized block design, we will try to implement the basic fundamentals for constructing the design, that is randomization, replication and local control. So, in this design we are going to use all the three principles of design, whereas in the case of CRD we were using only two, principle of randomization and principle of replication. And once you are going to get an outcome, now you have to think and tell me which of the outcomes out of the two, one for the block effects and one for the treatment effects, That is your here the different doses of medicine in which you are more interested. Think about it, and I will try to answer it towards the end of the lecture. So, let us begin our lecture and try to understand the randomized block design. Okay, so now you see that whenever we are trying to conduct an experimental design, we are essentially trying to test the different type of treatments, and we try our best that these treatments should be given to all the experimental units, right. Now, in case if the number of treatment is large that we want to compare, then obviously a large amount of experimental units are required, more number of units are required. So, definitely this is going to increase the variation among the outcomes responses, and in that case the setup of completely randomized design may not be appropriate to use. That may not give you a good outcome in terms of efficiency. Well, one can use, but it is not going to give us a efficient statistical inference. So, in such a case, when the experimental material is not homogeneous and there are suppose V treatments to be compared, then it may be possible to group the experimental material into blocks of size V units. So, if you try to see here, we are simply trying to do something so that we can reduce the heterogeneity, right, and we can achieve the homogeneity to the best possible degree, and now we have to think how to implement it. And one thing you can see here that when we are trying to consider the randomized block design, I am saying here there are V treatments and we have the blocks of size V units. So, there are two possibilities that you can give all the treatments to every block, or the second alternative is that you do not give all the treatments to every block. So, when we are trying to give all the treatments to every block, this is the setup of complete block design, and when we are trying to give say some number of treatments to the blocks, that means not all the treatments are given to all the blocks, then we have the setup of incomplete block design. Well, we are going to talk about incomplete block design later on, but at this moment I wanted to inform you that this randomized block design is going to be a complete block design. And why? Now, it is clear that we are going to impose a condition here that the size of the block, that means the total number of units in the block, they are going to be the same as the total number of treatments, right. So, now under the setup of randomized block design, the blocks are constructed such that the experimental units within the blocks are relatively homogeneous and resemble to each other more closely than the units in different blocks, right. Now, you have to first decide that how many blocks you want. Now, there is no rule, no statistical rule that how many blocks you have to create. It depends on the objective of the experimental conditions, the condition under which the data has been collected, and the nature of data. So, that is essentially the choice of experimenter, that the experimenter has to take a logical and correct decision about the number of blocks. But here we are assuming that there are a small e number of blocks. So, if there are B blocks, then we say that blocks are at B levels, and similarly you are trying to compare V treatments. So, we say that the treatments are at V levels, right, as you have done. Means if you have the medicine and you are trying to take 3 possible doses, 1 tablet, 2 tablet, 3 tablets. So, you say that the treatment is the medicine doses and there are 3 levels, 1 tablet, 2 tablet and 3 tablets. Similarly, if you try to say that we are trying to construct here 5 blocks, so that means every block will have its own effect, right, and they are going to be indicated by say effect 1, effect 2, effect 3, effect 4 and effect 5, and every effect is said to be as a level, and we say that there are 5 levels of the blocks. And now, if you try to see this the effect of the blocks are going to be same or different, that depends on the experimental conditions, right. For example, if you try to create a block of say small children and another block of elder people, yes, they are within homogeneous, but they may have different block effects, right. But definitely when you are trying to compare the treatments, your main objective is that you want to see whether the effects of different doses of the medicines are the same or not. So, you have to think, are you really interested in the block effects, but definitely you would like to have a comparison of treatment effects, because that block effects are not playing a significant role. Why? Have you ever heard that there is a medicine to control the body temperature, and this is going to be effective for Indian citizens and not for the American citizens, or say not for the say African citizens and so on? Not really. You want a medicine to be effective so that it is uniformly effective for all human beings of that age group, right. So, now what happened that we try to conduct the experiment, we try to divide the experimental units into different blocks, and we try to give different treatment to those experimental units, and we try to collect the observations say as y, I, j. Now, I and j, you know, there are going to be two subscript, one for the block effect and one for the treatment effect, and this reason goes to the same what we have done in the case of two-way analysis of variance, right. Do you remember that we had taken say small I is going from 1 to capital I and small j is going from 1 to capital J. So, now this I and j, they are going to indicate the block effects and treatment effects, right. So, now we are getting the observations or responses from the different level of blocks and different level of treatment, which are here B and V respectively. So, all these observations can be arranged in a two-way layout, and this observed data can be arranged as follows. For example, if you see here, I have created here a two-way table where I am writing here the blocks as a factor A is corresponding to your factor A of two-way ANOVA setup, and I am trying to take here the treatments as factor B here like this. So, now you can see here you are trying to group the experimental units into different blocks. So, those blocks are here numbered as here 1, 2, I up to here B, and these treatments they are also numbered as treatment number 1, treatment number 2 up to here treatment number J, somewhere here treatment number V, right. So, these blocks and treatments here like this, for example, if I say here this block number 1, this consists of all the people of the age 5 years to 20 years, and suppose and this treatment 1 is something like 1 tablet. So, now what are we going to do? We are trying to pick up one child from this age group of 5 to 12, and then we are going to give one tablet, and after that we try to record, for example, the time taken in bringing the body temperature to normal, and we write that value as y11. And similarly, now I take the second child from this age group of 5 to 12, and then I try to give the treatment number 2. For example, here treatment number 2 I can write down here say 2 tablets, and I try to give this 2 tablet to this child, and then I try to record the values y12, which is for example indicating the time taken in bringing the body temperature to normal. And similarly, I try to repeat it, and then we obtain here y1j, and finally we obtain here y1v. So, if you try to see what are we going to do, we have here v number of treatments, and we are trying to create a block of size v units. So, there are v number of children in the age group of 5 to 12, and then we are trying to give all the treatments to each of the child, and then we are trying to record their observations as y's, y11, y12 up to here y1v. And this is the way we try to conduct the experiment, and then we try to add them together. For example, if you try to add y11 plus y12 up to here y1i up to here y1v, and this is going to give us a sum which is called here as a block totals. So, this block totals B1 is giving us the value of the sum of all the observations in the block 1, right. Now, and this is here my block number 1. So, you can see here. So, block number 1 contains all the children between 5 years and 12 years. Well, that is the choice of the experimenter, whether the children between 5 years and 10 years are taken, or between 5 or 12 years are taken. That is the choice of experimenter, the way he or she wants to conduct the experiment. Now, similarly, we try to create here a block number 2. Say block number 2 can be say young children between 12 and say 18 years of age, and then we try to pick up one young child and we try to give the treatment number 1, that is 1 tablet, and we record the value as Y21. Then we try to give the second treatment, say 2 tablets here, and then we try to record the value of Y as Y22, and similarly we try to give the Vth treatment and we record the value as Y2V. So, this is the second block in which all the units have been given all the treatments. So, when we try to sum all these values here, then we get here the second block total, which is indicated by here B2. And similarly, I can do this exercise for all the blocks. So, one thing what you have to observe here, that we are trying to give all the treatments to all the unit inside the block. So, we need to have the block size to be the same as the number of treatment that we want to compare. And then finally, we have now all the block totals which I have written here. Now, you try to look at this table from this point of view in this way. So, what is really happening? Now, you are trying to see the experimental units which have been given the treatment number 1. So, these units are Y11, Y21, YI1 and YB1. These are the observed values or the values on the observations on the units which have been given the treatment number 1, that is 1 tablet. Right. So, what are you trying to do? You are simply trying to pick up the experimental unit from each of the block, and you are trying to see that which of the unit have been given the same treatment, that means treatment number 1 in block number 1, treatment number 1 in block number 2 and so on, and then you are trying to find out their sum. So, their sum is going to be indicated by here T1. So, this is actually Y11 plus Y21 up to here YI1 plus up to here YB1, right. So, this is your here treatment total, and you try to do the same thing for all the treatment effects. So, finally, you will have the value here T1, T2, say here TV, and somewhere it will be here Tj, where you are trying to sum all the units in your design which have been given the J treatment. So, now you have obtained this table in which you have arranged this data. Now, obviously, if you try to sum all the observation over here like this one, all the observations, which is equivalent to summing all the block totals B1 plus B2 plus here BB, or that is equivalent to summing up the treatment totals here, say here T1 plus T2 plus up to here TV. So, they are going to be the same, and they are going to give us the grand total G, that is the sum of all the observations in the design. So, now we have set up, there are 2 factors, treatments and blocks, and now we are ready for conducting the analysis of variance, right. So, now you can see what we have done here. This randomized block design, which is also called popularly as RBD, this is essentially a two-way layout, right, and in which you are trying to create the blocks, and in every block you are trying to give all the treatments. So, that is essentially a complete design. So, that is why sometimes it is also called as randomized complete block design, RCBD, or say RCB design. So, in this design, what are you trying to do? Within each block, the V treatments are randomly assigned to V experimental units, such that each of the factorial V ways of assigning the treatments to the unit has the same probability of being adopted in the experiment, and the assignment in different blocks are statistically independent. What does this mean? Means if you try to see here. Now, in this table, if you try to look in the say here block number I, where I am trying to make here a circle with red color. You have here say V number, V units, and you want to give here V units, you want to give V treatments. So, what are you trying to do? You are trying to allot any of the V treatment to any of the unit inside this block. So there are factorial V ways in which you can assign this treatment to this V units. So what are we trying to do? We are randomly allotting each of the treatments to the units inside the every block. And when we are trying to do it randomly, that means the probability of collection of every treatment could be given to every unit will remain the same. And this is how we try to use the principle of randomization here, right. So now this is the way you are trying to do the randomization in the randomized block design. So what are you doing? You are trying to number the V treatments as say 1, 2, 3, 4 V. Simply try to give a number and then randomly allocate the V treatments to V experimental units in each block, right. So what are we going to do here? Here I have just reproduced the same table here so that I can explain you once again. So you can see here that you are trying to take here say these many units inside a block and then you are trying to pick up a treatment at random and then you are trying to allocate it to any of the unit inside the block, where for the sake of representation I am writing here like as y11, y12, but if these are the any experimental unit which have been selected at random. So when you are trying to do it at random, that means the probability of selection of every experimental unit which can be given a treatment, that will always remain the same. So this is how we are trying to apply the principle of randomization. Now what about the principle of replication? If you try to see this treatment number 1, this has been given to a unit in the block number 1, it has been given to a unit in the block number 2, and finally it has been given to all the units in the block number 1, right. Now which unit is getting, that's a different thing. So now you can see that these treatments are going to be repeated in the entire design once in each of the block. So that means you can see here that treatment number V is occurring say here B times, treatment number 2 is occurring here B times and so on. So this is how we try to use the principle of replication. For example, here treatment number J is occurring in the block number 1 here, block number 2 here, block number I here and block number B here. So this is how we try to use the principle of replication. So now I can say that since each treatment is appearing in each block, so every treatment will appear in all the blocks. So each treatment can be considered as if replicated the number of times as the number of blocks, right. Now there are two possibilities that this number of replications for each of the treatment can be same or can be different. But when we are trying to talk about the randomized block design, then under this setup the number of blocks and the number of replication, they are always the same. That is what you have to keep in mind. Now in this RBD, do you think that are you also using the principle of local control? Yes. In this randomized block design, we are using the principle of local control in the following way. First, we are trying to form the homogeneous block of the experimental units and then we are trying to allocate each treatment randomly in each block. So this is how we are trying to implement this principle of local control so that we can reduce the variability. And so what will happen, that the error variance now will be smaller because of homogeneous blocks and some variance will be parted away from the error variance due to the difference among the blocks, right. Okay, now let me just give you here a very simple example that how this arrangement in a randomized block design will look like. Suppose we have here 7 treatments, we are trying to indicate them by T1, T2, T7, and suppose there are 4 blocks in which we want to conduct the experiment, right. So now you know that you need at least 28 units of experimental materials which is obtained from here 7 into 4, right. So one possible layout of the assignment of 7 treatments to each of the 4 blocks in the RBD can be here like this. So for example, you can see here I try to take here the block number 1 and I try to pick up a number say 2 and then I try to give the treatment number 2 to the first unit in the block 1 and can I try to pick up a random number from the table between 1 and 7. Yeah, if it is repeated, then I am going to ignore it and then suppose it comes out to be 7, then I try to give the treatment number 7 to the second unit and so on. I try to give here all the treatments to the units inside the block 1. Yes, obviously you can ask me what will happen to the last unit. Yes, you are left only with 1 treatment and 1 unit, so you have to give
that one to that unit. So, similarly, we try to give all the treatments here. You can see here 1, 2, 3, 4, 5, 6 and 7, all the treatment to the block number 2. And similarly, if you try to see here that treatment number here 1, 2, 3, 4, 5, 6, 7, they have been given to the block number 3, and similarly for the block number 4 also. So, this is one possible layout of an RBD in which we have 7 treatments with 4 blocks. Well, this layout is going to be different for different people, because the way the randomization will yield the number, because that a particular treatment is given to any unit, that will be changing because this is random, right. So, now we have got the data, we have learned how we are going to obtain this data, and now we come on the analysis of variance. So, now you can see here there are here 2 factors which are going to affect the outcome, which is one here is the block factor and say another is here the treatment factor, right. So, I can write down here the observations in the format of Yij. So, these are the individual measurements of a J treatment in the ith block. So, obviously, here I goes from here 1 to B and J goes from here 1 to V. Now, in case if you try to compare it with the two-way analysis of variance that you did earlier, you had taken the symbol like Yij, I goes from here 1 to here I and J goes from here 1 to here J. Now, this I is going to be replaced by B and J is going to be replaced by here V, and the entire analysis of variance that you did in the case of two-way analysis of variance without interaction will appear here, will be used here. So, it is very important for you that if you have not understood the two-way analysis of variance without interaction, that may create some hindrance somewhere. So, my request is that please try to move further only when you are clear about the two-way analysis of variance. So, now we have here the same assumption that Yij's are the independently distributed and they are following a normal distribution with mu plus beta I plus tau j and variance sigma square, right. Mu here is the general mean effect or the overall mean effect, beta I is the ith block effect and tau j is the j treatment effect, and then we are going to put here a constraint that summation beta I is equal to 0 and summation tau j is equal to 0. Now, you know that why these constraints are coming, otherwise you will not be able to estimate the parameters uniquely. Right, the parameters will not remain estimable, but now I do not need to explain these things again and again, but now you know how to conduct that analysis of variance. So, now because there are here 2 factors, so we are using here two-way analysis of variance. So, we are going to have here 2 null hypotheses, one for the block effects and another for the treatment effects, right. The hypothesis for the block effects can be written as say here H naught B means here blocks, say beta 1 equal to beta 2 equal to beta B is equal to 0, and the null hypothesis related to the treatment I am writing here at H naught T. T means treatment, which is here tau 1 equal to tau 2 equal to tau V is equal to 0, right. Now, what is your here the linear model in the case of two-way analysis of variance? That is simply going to be Yij is equal to mu plus beta I plus tau j plus epsilon ij. I goes from here 1 to B, j goes from here 1 to V, and epsilon ij are assumed to be IID, that is identically and independently distributed random errors following a normal distribution with mean 0 and variance sigma square. Now, you know that in case if you try to opt for the least square principle, then you will not need the normality assumption as long as you are doing the estimation, and you will need the normality assumption when you are trying to conduct the test of hypothesis, right. So, now in order to obtain the test statistics, you can use here the likelihood ratio test or principle of least square, whatever you want, and you are going to get the same outcome, and that I already had established. That I established that in the case of one-way analysis of variance, if you try to apply the likelihood ratio test and if you try to apply the theory based on principle of least square or the likelihood ratio test under the one-way analysis of variance setup, you are going to get the same outcome, right. So, now we just choose the principle of least square without any discrimination, right, means I have to choose one here. So, now you know how to employ the principle of least square. You first try to write down here the sum of square due to error, which is double summation I goes from 1 to B, j goes from 1 to V, epsilon square I j, which is equal to here double summation y I j minus mu minus beta I minus tau j whole square. And then we have to simply partially differentiate this S with respect to mu, with respect to beta I, and with respect to tau j. Now, do you think that I should do this differentiation here and then try to solve the normal equation? But I believe that since we already have done it in the case of two-way analysis of variance, so I do not need to do it again. So, I will leave it up to you, but I will simply request you that please try to do it again, at least for the sake of practice. So, now if you try to solve these three normal equations which are obtained after partially differentiating the sum of squares due to errors, or say sum of square due to random errors, then you try to impose the condition that summation beta I equal to 0, summation tau j is equal to 0, and then you can obtain the least square estimators of mu, beta I and tau j as follows. The least square estimator of mu will come out to be y bar double naught, the least square estimator of beta I will be y bar I naught minus y bar naught, and the least square estimator of tau j will be y bar naught j minus y bar double naught, right, where y bar double naught is the mean of all the observations. That is the same terminology. Then using the fitted model is obtained after substituting the values of the estimated parameters in the model. So, we can write down here y I j is equal to y bar double naught plus y bar I naught minus y bar double naught plus y bar naught j minus y bar double naught plus y I j minus y bar I naught minus y bar naught j plus y bar double naught, right. And then we try to square on both the sides of this equality sign, and then we try to take the double summation on both the sides, right. So, then we obtain here, for example, here if you try to see here, I am trying to bring this y bar double naught on the left hand side, and then I am trying to square, and then I am trying to take the double summation I goes from 1 to b and j goes from 1 to v. So, and then after that, if you try to do the same thing on the right hand side here, we will get here these three terms, this, and the cross product term will become 0. That you can verify very easily. So, the first term here is double summation y bar I j minus y bar double naught, this is here total sum of square TSS. The second term here v into summation over I y bar I naught minus y bar double naught, this is your here sum of square due to blocks. The third term here is the b into summation over j y bar naught j minus y bar double naught whole square, which is your here sum of square due to treatment. And the fourth term here is double summation y I j minus y bar I naught minus y bar naught j plus y bar double naught, which is your here SSE, sum of square due to errors, and their respective of the degrees of freedom. Now, you know, using the chi-square distribution with respect to the quadratic forms, you can write down very easily that the degrees of freedom for TSS are going to be PV minus 1, because you can see here that total number of observation that you indicated by n in the case of two-way analysis of variance, which is here B into V. Right. And similarly, the degrees of freedom for the sum of square due to block, this is B minus 1. The degree of freedom for the sum of square due to treatment, that will remain as V minus 1, and the degree of freedom for SSE will become B minus 1 into V minus 1. So, that is the same thing which I did couple of times earlier in the case of one-way, two-way analysis of variance. So, I am not going to give you here the detail, right. And also I had shown you that in the case of CRD also, that how are you going to obtain such degrees of freedom, because there are some constraints which are binding, and that is why you are trying to reduce the degrees of freedom by 1. So, that is not very difficult job for you. So, now you can see here that now I am just writing here all the expressions that we have obtained, because they are going to help you in finding out the F statistics based on the analysis of variance table. So, this TSS is going to be obtained here like this, that we have already done, and if you try to open it, this will come out to be double summation y square I j minus g square upon p into v, where g is here the grand total of all the observations, and g square upon BV, this is here a correction factor, that is called as like this. The sum of square due to blocks, which is obtained here like this, SSBL, and if you try to expand it, this will come out to be summation over I goes from 1 to B, BI square upon the number of blocks B minus the correction factor. This is here the correction factor, right. And where Bi here is given by summation over j Yij. This is the ith block total as we saw in the case of two-way layout. And then sum of square due to treatment we have obtained here like this, and this can be expanded as say summation over j goes from 1 to v t j square upon v minus g square upon bv, which is again the correction factor, where tj is the summation I goes from 1 to b Yij, and this is the jth treatment total. So, one thing I would like to show you here, that here in this case sum of square due to block or sum of square due to treatment, you are trying to use here this term correction factor. Well, if you try to see even this quantity I goes from 1 to b bi square upon b, that is also give you a sort of sum of square, but if you try to see, we are trying to adjust this quantity by g square upon bv, and if you try to see here that if you try to write down the terminology or the relationship that TSS is equal to SS block plus SS treatment plus SSE, possibly this correction factor will get cancelled out at a couple of places, but still we are trying to add it here, because you are going to use here the concept of chi-square distribution in finding out the distribution of the statistics. So, quadratic form has to be in the format of say y transpose A y, right, and you have some conditions on case here A, that A has to be an idempotent matrix, and then the degrees of freedom are going to be the rank of A. So, you want to convert this summation bi square upon b into a quadratic form such that it can be expressed in the format of y transpose A y, and the same thing you are trying to do with the sum of square due to treatment, that you are trying to write down here in the format of here y transpose b y. So, that should be clear to you. And then if you try to see the sum of square due to error, this is obtained here by this expression. So, there is no confusion. Now, using the theorem 7 and theorem 9, with that we did in the initial part of the lectures, where we are in the case of the development of analysis of variance, we had denoted them by quantities like q1, q2, etc. Using those results, we can write down here directly here that p minus 1 SS block upon sigma square follows a chi square into e minus 1 degrees of freedom, and similarly you can write down here like this, e minus 1 SSTR divided by sigma square follows chi square e minus 1 degrees of freedom, and similarly here you can write down the distribution for the SSE, right. Now, you can see here that under H naught B, your expected value of MS block will come out to be here the same as expected value of MSE equal to sigma square. So, that we already have done in the earlier part, and you can also show very clearly that sum of square due to block and sum of square due to treatment, they are independent. So, you can write down here that MS, that is the mean square due to block divided by mean square due to error, that will follow a central F distribution with b minus 1 and b minus 1 into v minus 1 degrees of freedom under H naught. Right. So, now you have got a decision rule for the block effect, and similarly for the treatment effects you can see here that under H naught t, your expected value of mean square due to treatment is the same as the expected value of mean square due to error, and both this SSTR and SSE, they are independent of each other, and based on that you can write down here the F statistics for the treatment effect as say mean square due to treatment divided by mean square due to error, that is following a F distribution with v minus 1 degrees of freedom and b minus 1 into v minus 1 degrees of freedom under H naught, right. So, now the decision rule for the two hypotheses for the block effect and the treatment effects comes out to be that the value of the F statistics, say here F for blocks and F for treatment, that is greater than say F at the tabulated value of F at respective degrees of freedom, and based on that you can take a decision whether your H naught is going to be accepted or rejected. Now, I try to address here a very simple issue which you have to understand. You see, when you started the randomized block design, what was your basic objective? Your basic objective was to test the efficacy of the treatment effects. You wanted to, for example, test whether the 1 tablet, 2 tablet or 3 tablet, they have got the same effect or they have got the different effects, right. But in order to test that hypothesis, you allotted different units to different blocks, or rather you created the blocks, and then you would like to see the way you have created the blocks, are they really needed or not, right. So, now in case if you have taken a decision for the null hypothesis for the block effects and treatment effects, there are two possibilities that either or both these hypotheses are going to be accepted or not. So, if they are not accepted, obviously you will try to choose the multiple comparison test appropriately, and you will try to divide different this population into different blocks, right. So, if you try to see here, if H naught B is accepted, what does this actually mean? Then it indicates that the blocking is not necessary for the future experimentation, right. Or the way you have created the blocks, you can say that all the blocks have got the same effect, right. And in case if your the null hypothesis for the treatment is rejected, then it is going to indicate that the treatments are different, right. Now, the question will be that which of the treatments have got the same effect and which of the treatments have got the different effect. So, for that you can go for the multiple comparison test and try to divide the entire set of treatments into different subgroups, such that the treatments in the same subgroup have the same treatment effect, and those in the different subgroups, they have got the different treatment effect. For example, if you try to see, suppose you see that either one tablet is given or two tablets are given, they are going to take the same time to bring the body temperature to normal. So, that means practically the effect of one tablet and two tablets are the same. So, it might be possible that the doctor may say that okay, then why to use two tablets if the tablet has got the same effect, and why not to use only one tablet to control the body temperature, right. On the other hand, if you try to see on the many prescriptions in the medicine, it is written, for example, in the case of different types of liquid medicine, that okay, half teaspoon for children, 1 teaspoon for this age group, and say 2 teaspoon for this age group, and so on. So, what does this mean? For example, if somebody says that okay, between the age group of say 5 years to 12 years, only 1 teaspoon of the medicine has to be given, that means either you are trying to give 1 teaspoon to a child of 5 years, 6 years, 7 years, 8 years, 9 years, or say 10 years, anybody in this age group, the medicine is going to have the same effect. But in case if you try to give the 1 teaspoon to an elder people in the age group of say 25 to 35 years, then this may have a different effect, and it may be possible that we know from the common sense that the medicine may not be effective, right. So, this is the type of decision what you are going to take. So, now finally, whatever you have done, all these results can be combined in the form of an analysis of variance table, and so this table will have the source of variation from blocks, from treatments, from errors, and from total, that is the sum of its square due to total will be sum of its square due to block, sum of its due to treatment, and sum of its square due to error, right. And the corresponding degrees of freedom for the sum of square due to block, they will be p minus 1. For the sum of square due to treatment, this will be v minus 1. For SAC, this will be b minus 1 into v minus 1. And for the total sum of square, this is bv minus 1. And based on that, you can obtain here the mean square. So, mean square due to block will be SS block divided by degrees of freedom. So, similarly, you can obtain here the mean square due to treatment, say here that will be here sum of square due to treatment divided by the degree of freedom v minus 1, and similarly you can obtain here the MSE at SSC divided by the degrees of freedom, right. Now, in case if you try to take the ratio of mean square due to block and say MSE, you will get here a F statistics for the block effect, and if you try to take the ratio of mean square due to treatment with respect to the mean square error, then you will get here the F statistics for the treatment effect, and based on that you can take an appropriate decision to accept or not the null hypothesis. And similarly, if you try to find out the expectation of the here different mean squares, I am not giving you here the proof, because the proof is very similar to what we have done earlier in the lectures. So, this expected value of MS blocks will come out to be sigma square plus V upon B minus 1 summation beta I square, and similarly expected value of mean square due to treatment will come out to be sigma square plus B upon V minus 1 summation tau j square, and expected value of MSE will come out to be same as sigma square. So, you can see here that in this case also an unbiased estimator of the sigma square is being provided by the MSE, and in case if your H naught B is accepted, that means all beta I is 0, that means this term is going to be 0. So, this is going to be only here the same as sigma square. This is what we mean when I wrote here this term here, you can see, right, this term here when I wrote means I meant the same thing. And similarly, if you try to see that if your all treatment effects are the same and H naught T is getting accepted, then this term summation over j tau j square will become 0, and then you will get here simply here expected value of MS treatment as a sigma square. So, these expectations are also trying to conclude the same thing what you have concluded using the null hypothesis. Right. So, now we come to an end to this lecture, and you can see here we have explained and we have understood here the concept of randomized block design. And now in a simple words I can say that whenever you are trying to deal with two factors where you have to use the two-way analysis of variance, then randomized block design setup is compatible with that setup. And in randomized block design, you are trying to divide your experimental units into different blocks, and then you are trying to conduct the analysis of variance. You are trying to test whether the treatment effects are going to have the same effect or they are having different effects, and based on that you can take the appropriate decision. So, now you have done one design, that is CRD with one effect, this RBD with two effects. Now, what will happen with three factors, right? So, that is the Latin square design that we are going to discuss in the next lecture. So, you try to revise this lecture, try to understand it, try to practice it, try to solve the problem, and I will see you in the next lecture with Latin square design. Till then, goodbye.